One of the biggest roadblocks for new embedded programmers is hardware. With the confusing amount of options available, none of which are free, getting hardware to learn on is often a hard first step to overcome. Luckily, with QEMU or QEMU, you can skip the hardware and learn embedded code right on your desktop. In this video, I'll show you how to set up an embedded Rust project and run the code without access to a development board. Before we start, hit that sub button to be alerted when I put out new videos like this on a weekly basis. So to get started here in our no hardware Rust embedded adventure, step one, we have to do a little bit of project setup. To set up our project, we're going to use this repo here, the Cortex M Quick Start GitHub repo underneath the Rust embedded user on GitHub. So this project is a cargo repo that is set up with a bunch of dependencies to be able to quickly produce binaries that are able to be ran on the Cortex M0 or 3 processor. Luckily, this project also has rules in the cargo files to do QEMU emulation with those binaries if you don't have the board. So I'm going to show you guys how to use this repo and get it set up to do that kind of development. So we'll do git clone on that repo, and I'm going to call it Rust no hardware because that's the whole point of this video. We'll clone that down. Should clone pretty quickly. It's actually pretty lightweight. We'll go into that folder, Rust no hardware, and run Sublime in that folder. So there are a few changes we have to make this project able to be ran as it currently is set up, right? So to edit this project, we need to add a few things. Step one is the author. So the author is me. I'm always the author of my own code, obviously. And then name the project something fun, like app, very, very boring, normal title. Okay, take this app here and also copy it down in the bin area to the name of your binaries. Call them app as well. So with those changes, you can actually build a program right now that would build for the Cortex ARM M3 processor. We need to actually check out what program we're building, right? So if you go to the source folder here and go to main.rs, we're going to kind of walk through line by line what this code is doing. This is actually pretty different than normal Rust. If you're only used to building Rust for a regular like Linux environment, there are a couple major changes to the structure of the program, and we'll walk through them line by line. So line one here, normally in Rust, when you build a program, you use the standard library. The standard library brings in libc and all this other kind of, not bloatware, but just heavy code that normally an embedded chip can't handle. So by saying no standard, we replace the standard library with the core library, kind of a more lightweight version of the Rust backend. Then we say no main. Normally when we use the standard library, it looks for a main function, and instead we're going to say, hey, we don't necessarily need a main function. We'll take care of that elsewhere. Line 5, we are setting up a panic handler. So when the board has a panic and an event that it can't handle via error handling, we need to tell it what function we're going to run. And on line 5, we say use the panic halt function that comes from the Cortex M library. Then we do two dependencies, Cortex M assem for assembly inlines like assembly nop, and then line 12 we use the Cortex M entry point idea, right? So on line 14 we actually use that entry. So before we said we don't go to a main function, we will specify the entry point of the board. On line 14 we say, hey, the entry point, the first function to be ran, is this main function here. On line 16, we run an assembly nop to kind of give main some code to contain, and then we end it with an infinite loop because in embedded programming, the board doesn't exit, it just runs forever. So if our code ends, we get to this infinite loop state. That's also seen here on line 15 with the returns exclamation point. In Rust, that actually means that the board does not return. It just doesn't. That's like the none. It's not a none type, but it's like a none type. So we want to actually make this code do something more meaningful. So we're going to actually get rid of the assembly dependency here in line 16. And then we're going to, from another dependency, we're going to say use Cortex M semi-hosting. So this idea of semi-hosting is what we're doing here, where we're building the program for a different target, like a Cortex M processor, for example, but with the idea being that we're going to run it locally. That's the idea of semi-hosting. And within the semi-hosting library, there are two things we need. The first being debug, and the second being host print line. That's a macro, by the way, and we'll put a semicolon at the end of that line. The debug library allows us to do things like exit or return from the board, which in embedded doesn't actually happen. But when you're semi-hosting, you want to be able to say, hey, at this location, end the program cleanly, just wrap it up. And then H print line is host print line, which says if you're doing a semi-hosting environment where you are hosting it in an emulated environment, on the host, forward to the host a line that you're going to print to standard out. So that's kind of the idea behind semi-hosting. So here we're going to use that host print line function, and it's actually a macro, so we'll end it with an exclamation point, and then treat it like a function, kind of like printf, and we'll say hello world, exclamation point, new line. And then don't forget, as a standard Rust-ism, I have to unwrap your result to make sure that it didn't return no value. And then after that, we're going to do our semi-hosting debug. We're going to call the exit function, and we're going to return the exit success value. And again, all this does is, in the event that we are doing a semi-hosted environment in QEMU, this will end the program here as opposed to going into an infinite loop, right? So that's kind of useful if you're doing something that you are running in an emulated environment. So now that our project is set up and we have some code to run, the next thing is how do we build this code? So first off, like I said before, this is getting built for a Cortex M0 processor. You need to make sure that you have the build chain in Rust up to compile down to that architecture. So to get that, we're going to do rust up target add thumb v7 none EABI. So we're going to copy that target to our clipboard and we're going to run this command. I already have this build chain installed, but for you guys, if you don't, it may take a second to pull down the build chain and get that put into your rust up, package handler. So once we've done that, now what we can do is tell cargo to build and build it for the target, that target up here. And once we do this, what'll happen now is cargo is running through the configuration file, the cargo.toml, and it's running through all the dependencies and figuring out what dependencies and sub-dependencies it needs to be able to build our program. So after it goes through, it builds these, it compiles them all, it'll finally, at the end of the program, spit out our binary. And I'll show you guys what that looks like when it's all wrapped up. Awesome. So now that we've, built our program, finished dev, notice that there are no errors. We can actually go look at our program by going to target, thumb, that's the target name, and then debug, that's the release we're doing. And then here, file app is our program, right? This is the output of our program, and it's a 32-bit ELF compiled for ARM EABI v5. What we can do is we can use the ARM regular build chain, not the Rust build chain. We're in a flat binary now, not a flat binary, but we're in a binary format now. We can use object dump to dump out the application and kind of check out and see what it's doing. So here in object dump, we see that we have the reset vector. This is when the board starts up, it does something. And this is it setting up the board using the Cortex M3 library. And eventually, once we get done resetting the board and getting it all set up, we go to our main functions. We can go to main, and here is where our main happens. And eventually you see that it calls the semi-hosting, standard out print function. So pretty cool. Now, we have this program, but in this video, we don't have a board. We have no board we can compile it to. Luckily, this project, the Cortex M Quick Start project, has a little hack we can do to run the program without having the board. So if you go to the config.toml file, you'll see in the description for the target we're building for, the thumb v7m, we actually have a hidden runner command here. So again, in Rust, runners are things that instead of you saying cargo build, you say cargo run, it will run this program. We're going to use the QEMU system ARM with the CPU being set to the Cortex M3 to run our program without actually having the board. So that's pretty awesome. Go check that out real quick. So we do cargo run tac target, this target. And you see here, it gets done building it again, and then it runs our program with that command, and we see hello world being ran. So that's pretty awesome. We're able to run our program without actually having the board. But what does that actually do for us? Well, in the event that we wanted to try to do something new that may break, we need to have some kind of introspection on the board to figure out what's breaking or what's crashing. So QEMU actually has a really easy interface for using GDB in our functions or in our programs. We can go over here in the QEMU command line. We could say tac gdb TCP :3333. That's going to be the port it listens on. And then we can also say tac s. So what the tac capital S does is it freezes QEMU when it starts up, so we can connect to it with GDB. So we'll kind of test that out real quick. We'll do the run again. I didn't save the config file. We'll do the run again. Cool. So now it's hung. It's waiting for us to connect with GDB. And then in a new window, we can say GDB multi-arc and then our app. So it's loaded our app into GDB, and now what we're going to do is say target remote localhost. Actually, we do TCP // localhost 1234. That's the port we specified in our command over here. Cool. So what we've done now is we've connected to our target localhost 3333. We are in the Cortex MRT reset variable, the reset function, because again, the board is in a frozen state. And now we could debug it if we wanted to, right? We could say lay next. We can get kind of the function that we're in within Rust. We can do lay next and get the assembly version of that. We can get the register state. We'll just type continue, C, and eventually the program runs. And over here on the left, we get hello world because the program ran and then exited. So this is pretty cool. I think if you're new to Rust or you want to kind of learn something embedded, but you don't want to just go back to C, you want to learn a new thing, I think Rust is a good place to start. A lot of times people have a hard time getting into this realm because they don't have the hardware to do it. So by using QEMU, you can get into it pretty quick. And I think this project here, the Cortex M Quick Start, is a good place to start. So if you guys like this video or you learned something, do me a favor, hit like, hit subscribe, and go check out the video linked here. We'll see y'all in the next video. Take care.